Hello and welcome to Earthly Teachings. I'm your host, and today we're diving deep into Electrotechnics N4. Our focus will be on Unit 4.2, the no-load condition of a transformer. By the end of this tutorial, you will be able to, firstly, describe the concept of a transformer on no load. Secondly, identify the circuit and vector diagrams for this condition. And thirdly, perform key calculations related to no-load operation, which is essential for your exams. Let's get started and demystify this important topic. First, let's understand what the no-load condition actually means for a transformer. During no load, the secondary winding is left open-circuited. This means the transformer is connected to a power supply, but there's no load connected to its output. Even though the secondary is open, the transformer still draws a small current from the supply. This small current, known as the no-load current, is not for powering a load, but for something else. Its function is to supply the power required to cover the constant losses inside the transformer. These are primarily the iron losses in the core. So, because the secondary winding is open and there's no load, the transformer's output power during no load is, by definition, zero. An important point to remember is that even in an open circuit test, the primary circuit is complete. The transformer is connected to a voltage source, which is why a current still flows through the primary winding. This current is necessary to establish the magnetic flux in the transformer's core. Now, let's visualize this with an equivalent circuit diagram. An equivalent circuit simplifies a complex device, like a transformer, into standard electrical components. It's a representation of the transformer where its resistance and leakage reactance for both the primary and secondary windings are imagined as external components, making the analysis much easier. Here's the equivalent circuit diagram of a transformer on no load, as shown in Figure 4.1. Let's break it down. On the left, we have the primary side. V sub 1 is the primary voltage, R sub 1 is the primary resistance, and X sub 1 is the primary leakage reactance. The no-load current, I sub 0, flows through these components. Now, let's look at the parallel branch. This is the heart of the no-load analysis. It's connected to the primary induced electromotive force, E sub 1. The resistor in this branch, R sub C, represents the core losses. The inductor, X sub M, represents the magnetizing reactance, which is responsible for creating the magnetic flux. These two are in parallel. The no-load current, I sub 0, splits into two components. The core loss current, I sub C, which flows through R sub C, and the magnetizing current, I sub M, which flows through X sub M. Finally, on the right, we have the secondary side, which is open-circuited. As you can see, the output is 0, and the secondary induced EMF, E sub 2, appears across the open terminals. So, to recap, this diagram clearly shows how the no-load current is broken down into its two crucial components. Understanding the circuit is one thing. Seeing the phase relationships between voltage and current is another. For this, we use a vector diagram. This is the vector diagram for a transformer on no load, Figure 4.12. Vector diagrams are essential for understanding AC circuits. Let's build this diagram step by step. First, we draw the magnetic flux, phi, as our reference vector along the horizontal axis. This is because the flux is common to both primary and secondary windings. The magnetizing current, I sub M, creates this flux. In an ideal inductor, current lags voltage by 90 degrees. Here, the flux acts like a voltage. So, the magnetizing current, I sub M, is in phase with the flux, phi. Now for the induced electromotive forces. By Lenz's law, the induced EMF opposes the change in flux. This means the induced EMFs, E sub 1 and E sub 2, will lag the flux by 90 degrees. So, we draw them along the negative vertical axis. The primary applied voltage, V sub 1, must overcome the primary resistance and reactance drops. For a simple analysis, it's often drawn 180 degrees out of phase with E sub 1, as shown, because V sub 1 is the cause and E sub 1 is the effect. Next, the core loss current, I sub C. This current supplies the power losses. Power is real, so I sub C must be in phase with the real component of the voltage, V sub 1. So, we draw I sub C along the positive vertical axis in phase with V sub 1. The no-load current, I sub 0, is the vector sum of the core loss current I sub C and the magnetizing current I sub M. Finally, the angle between the primary voltage V sub 1 and the no-load current I sub 0 is called the no-load phase angle phi sub 0. This vector diagram is a crucial tool. It visually explains the phase relationships that govern transformer operation. Now that we understand the diagrams, let's connect them to the mathematical formulas we need for calculations. We'll use the diagram we just drew. First, the no-load current, I sub 0. As we saw, it's the vector sum of two components. The magnetizing component, I sub M, is the horizontal component of the no-load current. From the right-angled triangle formed by I sub 0, I sub C, and I sub M, we can see it's given by I sub M equals I sub EO times the sine of phi sub 0. This formula, I sub M equals I sub 0 sin phi sub 0, calculates the current component that creates the magnetic flux. It's the reactive component. Next is the core loss component. The core loss component, I sub C, is the vertical component of the no-load current. Looking at the same triangle, we can see it's given by I sub C equals I sub 0 times the cosine of phi sub 0. This formula, I sub C equals I sub 0 cos phi sub 0, calculates the current component that supplies the power losses in the core. It's the active component. The no-load power, also known as the iron losses, is calculated like any AC power. The power on open circuit P sub 0 is the product of the primary voltage V sub 1, the no-load current I sub 0, and the cosine of the phase angle phi sub 0. Finally, the secondary induced EMF. On no load, since there is no secondary current, there are no voltage drops across R sub 2 and X sub 2. Therefore, the secondary induced EMF, E sub 2, is exactly equal to the secondary terminal voltage, V sub 2. These formulas are the tools we need to solve any no-load problem. Let's put them into practice. We'll begin with a worked example. This is example 4.1 from your notes. Pay close attention to the step-by-step process. The question is, a single-phase transformer draws a no-load current of 2.75 A at a power factor of 0.45 lagging from a 400 V supply. Calculate A, the magnetizing current, B, the core loss component of the no-load current, and C, the power on open circuit. First, let's write down what we are given. The no-load current I sub 0 is 2.75 A. The no-load power factor cosine phi sub 0 is 0.45 lagging, and the primary voltage V sub 1 is 400 volts. Let's solve for the magnetizing current, I sub M. The formula is I sub M equals I sub 0 times the sine of phi sub 0. We know I sub 0, but we don't know phi sub 0. However, we know the cosine of phi sub 0 is 0.45. We can find the angle phi sub 0 by taking the arccosine, or inverse cosine, of 0.45. This gives us approximately 63.26 degrees. Now we can substitute the values into the formula. I sub M equals 2.75 times the sine of 63.26 degrees, which calculates to 2.456 amperes. So, the magnetizing current is approximately 2.46 amperes. We're continuing with example 4.1. Let's find the second part of the question. Next, we need to calculate the core loss component of the no-load current, which is I sub C. The formula for I sub C is I sub 0 times the cosine of phi sub 0. This one is straightforward, as we are already given the power factor, cosine phi sub 0, as 0.45. We can substitute the values directly. I sub C equals 2.75 times 0.45. This gives us 1.2375 amperes, which we can round to 1.24 amperes. Finally, let's calculate the no-load power. The last part is to calculate the power on open circuit P sub 0. The formula is P sub 0 equals V sub 1 times I sub 0 times cosine phi sub 0. Again, we have all the required values from the question. P sub 0 equals 400 volts times 2.75. Amperes times the power factor of 0.45. Multiplying these together gives us exactly 495 watts. This is the iron loss of the transformer. And that completes our first worked example. You can now see how to apply the formulas we learned. Now, let's tackle a question from the activity section to deepen our understanding. We'll look at question 6. The question states, a transformer working on no load draws 2.5 amperes from the supply at a power factor of 0.3 lagging. We need to calculate the no-load phase angle, the magnetizing component, and the core loss component. First, let's identify our given values. No-load current I sub 0 is 2.5 amperes, and the power factor cosine phi sub 0 is 0.3 lagging. Part 6.1 asks for the no-load phase angle. We know the power factor, so we can find the angle using the arcs cosine function. Phi sub 0 equals the inverse cosine of 0.3, which is 72.54 degrees. This is the angle by which the no-load current lags the primary voltage. Next, part 6.2, the magnetizing component. Using the formula I sub m equals I sub 0 sin phi sub 0, we substitute the values. 2.5 times the sine of 72.54 degrees. This gives us approximately 2.38 amperes. And finally, part 6.3, the core loss component. Using the formula I sub c equals I sub 0 a qs phi sub 0, we have 2.5 times the cosine of 72.54 degrees. This is the same as 2.5 times the power factor of 0.3, giving us 0.75 amperes. This example reinforces the application of the formulas. Notice how the power factor is used directly in the I sub c calculation. Let's look at a slightly different problem, question 7, from the activity. This time, we're given the components and have to find the total. The magnetizing and core loss components of the no-load current are given as 4.105A and 1.1A, respectively. We need to find the no-load current, the no-load power factor, and the power on open circuit if the supply voltage is 1000 V. Let's list what we know. The magnetizing component I sub m is 4.105A, and the core loss component I sub c is 1.1A. First, part 7.1, the no-load current. Since I sub 0 is the vector sum of two components that are 90 degrees out of phase, we can use the Pythagorean theorem. I sub 0 equals the square root of I sub m squared plus I sub c squared. Substituting the values gives the square root of 4.105 squared plus 1.1 squared. Calculating this gives a no-load current I sub 0 of approximately 4.25 amperes. Now for part 7.2, the no-load power factor. The power factor, cosine phi sub 0, is simply the ratio of the core loss component to the total no-load current. So it's 1.1 divided by 4.25, which gives a power factor of approximately 0.29. Finally, part 7.3, the power on open circuit. This time, the supply voltage V sub 1 is 1000 volts. The formula is P sub 0 equals V sub 1 I sub 0 cosine phi sub 0. We multiply 1000 volts by the current we found, 4.25 amperes, and the power factor we just calculated, 0.259. This gives us approximately 101.3 watts, or 1.1 kilowatts. This demonstrates how the iron losses of the transformer change with the supply voltage. Let's quickly recap what we've covered and confirm our learning objectives. We started by describing the no-load condition, where the secondary of a transformer is open-circuited. We saw that even then, a small no-load current flows to cover the constant iron losses, and the output power is 0. We then identified the key diagrams. The equivalent circuit showed us the two components of the no-load current, the core loss current I sub c and the magnetizing current I sub m. The vector diagram illustrated their 90-degree phase relationship and how they sum to the total no-load current. Finally, we performed key calculations for these components and the no-load power using the essential formulas. I sub c equals I sub 0 cosine phi sub 0, I sub m equals I sub 0 sine phi sub 0, and the power formula P sub 0 equals V sub 1 I sub 0 cosine phi sub 0. Understanding the no-load condition is a fundamental step in analyzing any transformer. You can now describe this condition, read its diagrams, and perform the essential calculations. Thank you for watching Earthly Teachings. Subscribe for more Electrotechnics N4 tutorials and revision lessons to help you succeed in your studies.